Hi everyone, my name is Mabulaya Mukakabia and I'm your e-teacher for the course Strength of Materials 401M. In the following video, I will explain an example from chapter 6. This video was requested by a student also studying the same course. Feel free to request more videos and I will do my utmost best to record as many videos as possible and as fast as possible. Please note the title of the textbook, its author, and the edition number. Okay, in this example, we are given an unsymmetric. In this example, we're given an unsymmetric cross-section of a beam, and we're asked to calculate two things: normal stresses at various points of the cross-section beam, that is A, D, B, and E, and also to locate the neutral axis there. Okay, so first let us read the question. A Z section is subjected to bending moment of 3 kilonewton meters at an angle of theta is equals to negative 20 degrees to the z-axis as shown. Find the normal stresses at points A, B, D, and E, and the corresponding A prime, B prime, D prime, and E prime respectively, and also find the position of the neutral axis. Use the following numerical data. H is equals to 200, that is the height, and B equals 90 millimeters, the thickness equals to 15 millimeters. Okay, I would like to help you establish a systematic approach to calculating the normal stresses that we've been asked to calculate. And a systematic approach simply means that you follow a clear procedure of steps in order to determine the solution, of which in this case must be the normal stress. So if you attempt to calculate the normal stresses using the applicable equation, you will notice that you do not have all the information that you need to calculate the solution. You will immediately notice that you must determine the moment of inertia first. Therefore, we start by calculating the moment of inertia about the z-axis and the moment of inertia about the y-axis. In this example, the value of Iz and Iy are copied from example 12.7 from chapter 12. And for the benefit of our understanding, let us now determine how Iz and Iy were calculated. Iz and Iy, this shown there, are the transformed Iz and Iy, as shown there, are the transformed moments of inertia and are calculated using equation 1228, 1233, and 1236. Allow me to explain what I mean when I say Iz and Iy are the transformed moments of inertia. In normal circumstances, where the z-section is not tilted, as we can see in our example here, Iz and Iy are straightforward and simple to calculate using standard equation of moments of inertia and the parallel axis theorem for areas that are offset from the neutral axis. To read more about the parallel axis theorem, please refer to chapter 12.5. In our case here, the z section is tilted. Therefore, our moments of inertia must also be transformed into the iz and iy that we see here, such that they are a true representation of our z section here and its orientation. Let us now calculate the moments of inertia of the z section when it is not tilted. After that, we will transform the moments of inertia that we have calculated into the transformed moments of inertia iz, iy of a tilted z section. Now, when having a look at this z section here, for example, which is not tilted, first notice that the x-axis in this example 12.5 corresponds to the z-axis of example 6.8. This is important. Please keep it in mind for later. Now, before I explain why I put these two equations here in this slide, let us first read the first part of this solution here. Particularly this sentence here. It says the moments and products of inertia with respect to these axes, and these axes they're talking about is the y-axis and that y-axis there. They're saying the moments and product of inertia with respect to these axes can be obtained by dividing the area into three rectangles and using the parallel axis theorem. The result of such calculation are as follows, and this leads to why I put these equations here. These are the equations from the parallel axis theorem. They allow you to calculate the moment of inertia for areas that are offset from the principal axis. For example, since here in this solution here, we are told that we can find the moment of inertia of this z section by splitting this section into three rectangles. We're going to end up with this rectangle and that rectangle being offset from the principal axis being x and y. And for them, we'll use the parallel axis theorem to calculate them. Okay. And just to help you understand what these values, what IXC and IYC mean, and D1 and D2 mean, I'm just going to draw a quick sketch, but you may please refer to my first video to understand how the meaning of these variables. But I'm just going to make a quick sketch now to explain the problem. That. I hope that is good enough. Let's try that again. So let's say this is our Z section and we want to divide it into three parts. That will be rectangle 1, 2, 2, and 3. And our principal axis sitting there is y, and x. And okay, and basically when they say IXC, the moment of inertia for an area that is offset, so if we are looking at this rectangle here, what it means that if we want to calculate its local moment of inertia, we will have to look at its local coordinate system. I'm just going to do it in dotted line. That will be your YC. That will be your XC. And the same applies to this one here. So this axis is exactly in the middle of, it's exactly in the middle of this length here of the rectangle, and the same applies to this axis here. It's at the middle of that side of the rectangle. And the important thing is that D1 is basically the distance between the neutral axis, the local neutral axis. In this case here, IXC means the distance between this axis and this global axis. I'm just gonna write, indicate here quickly what D1 is. So it means from there to there. That is our D1. And if we look at the second equation here, D2 will be the distance between the local neutral axis of the Y. And let me just indicate quickly. The D2 will be the distance between the YC, that YC, and this one here. So it will be basically be like that. Just give you a different color. So that is D2. This is just to help explain the just to help explain what the variables stand for in this equation. And once we've done that, we have now basically calculated the untransformed moments of inertia, and we are ready to use equation 1233 and 1236 to finally transform our moments of inertia so that they are true representation of our our tilted Z section. So we want to transform this IX and IY. So we know how to calculate IX. We know what the area is the area of each rectangle. This one is an easy one. Let me just indicate. So this is also another rectangle. We know how to deal with this one, and we substitute all the required information into this equation here, and we calculate the total moment of inertia, and we end up finding IX and IY. Now that we've calculated the untransformed moments of inertia, we're ready to use equation 1233 and 36 to finally transform these into our true representation of the tilted Z section. Okay, so when looking at our equation 1233 and 1236 for transforming our inertia, our moments of inertia, we see the untransformed terms IX there and IY, which we have just calculated. The term IXY is the product of inertias and is calculated using the equation 1228 as shown there. The equation also requires knowledge of theta as is shown there, and theta p, by the way, is the angle with which the z section is tilted. So let us calculate angle theta p, because remember that we are given the angle theta, not angle theta p. Angle theta is the angle at which the moment, total moment, is applied onto our z section. But angle theta p is different. It is the angle at which our section is tilted away from the untilted or original position. So let us calculate theta p. Equation 1239 gives the relationship between theta p and the untransformed moments of inertia. And the equation 1239 is shown there. So we want to calculate angle theta p, and there is the formula there. And after calculating theta p, we substitute into the previous equation of 1233 and 36 so that we finally calculate the moments of inertia. So now we have solved our moments of inertia and we are ready to proceed to calculating the normal stresses. So we have transformed our moments of inertia. We are now ready to calculate the moments of inertia. Just a quick word of advice. Please be careful of your units, be consistent, and do not mix millimeters and meters in the same equation, or mix megapascals and gigapascals. Rather use pascals or megapascals only. Just choose one and stick to it. If you're still not comfortable with units, please ask on our UNISA discussion forum and we will provide you with assistance. We have calculated our moments of inertia, that is IZ and IY. Look at our coordinate system. It is ZY coordinate system, not XY coordinate system as in the example from chapter 12, which is 12.7. But this is no need to worry about it. It is just different notations or labeling. So this means our transformed IX, or moments of inertia about the X from the previous example, is indeed actually the same as the moment of inertia about the Z-axis here. So that one here, it should be the same as the moment of inertia about the X-axis from the previous example. And the moment of inertia about the Y still stays the same, because the y-axis here corresponds directly to the y-axis in the previous example. Now we must calculate the normal stresses at each points A, B, D, D prime, E, and E prime. The direction of our total resultant, the total or the resultant bending moment, this one here, is at an angle as shown in this figure. This requires of us to break the resultant bending moment into two components, mz and my. This will make it easier for us to know the direction either positive or negative, of the normal forces acting at one point due to each component of the bending moment. As usual, we know that the flexure formula for calculating normal stress at a point requires the distance from the principal axis. Likewise, we must now determine the x and y coordinates of each point A, B, D and D prime, E and E prime. Now, we will use a little bit of our analytical geometry and trigonometry from high school to determine the x and the y coordinates of each of these points. I will calculate the x and the y coordinates of just a few points for you to demonstrate the important points that you need to consider in order to arrive at the correct solution. Let us first start by calculating the x and the y coordinates of point A. Okay, now we want to first start by calculating the coordinates for point A. Okay, so starting off by calculating the y, that is the vertical distance from A, the vertical distance. For us to do that, we know this distance, we know that angle, we'll calculate it just now, and we know we can also calculate that. This will allow us to calculate that distance. Now, let me just illustrate what I'm talking about quickly. So, the first thing that we need to know is, since we've calculated our theta p, we know that our theta p is equals to 19.2 degrees. Okay, and we know that we also know that this angle here is supposed to be 90 degrees. Therefore, this angle here between this axis, that angle which is alpha, must equals to 90 degrees minus 19.2 degrees. For now, we'll just refer to it as alpha. You will notice in the solution that they used theta p mostly and not alpha. So, how is this going to help us? I'm going to delete this part here, just so it doesn't clutter around quickly. So this here is 90 degrees, we know that. And so to get this height here, we're going to look at this triangle. We know that distance, and we want this height. This is what we're looking for. So we end, in fact, that means we have this kind of a rectangle. Oh, sorry, that. This is the kind of rectangle, the triangle that we have. We know this angle here is alpha, but here is our theta p. Okay, and we know that this is h over 2, and we're looking for that side there. And this is we know that we can easily calculate this. That is, by using Pythagoras, is h over 2 just retry that again. That will be h over 2 the cos of theta p, that will give us that distance there. And now we're not done, because we have only calculated this distance from that point there going down. What are we now left with? We're left with the distance from that point there to somewhere there. We need to calculate that vertical distance there to determine the vertical or the y coordinate of A. So what we will do is this, like that, and this guy. This is what we are looking for. Now, we know this distance. We know that distance there from this point up until this corner here, but not that one. Our triangle starts there and not there. So we want to calculate, we want to use this length in this triangle to calculate this distance. Now the question is, what is that angle there? Okay, so if you look at this theta p, it should be, that must be equal to that, vertically opposite angles. And if you look at this line here, is parallel to that line there, obviously. And we're saying this line has a particular angle with respect to the horizontal. That angle is theta p. That one has a particular angle with respect to this, which is also a horizontal. And that angle will obviously have to be theta p as well. So these two are equal. So we have theta p here. Well, okay. So what does this mean? It means that once we know that distance, which is basically the b, which is the entire length, subtracting half of that thickness there will give us that distance. I'm just going to write it down quickly. So this is b minus the thickness over 2, which is the half of the thickness. That will give us that distance. It will give us the distance from there up until there. Excuse me for my terrible drawing. Okay, so what does this mean? It means now for us to find that vertical part, we can just say that is equals to b minus t over 2 and the sine of theta p. Hope that's feasible. And we now have to add both of these. We have to add this distance, which is b minus t over 2 sine theta p, and that part. And it will look something like this. Therefore, we'll say the y coordinate of A is equals to h over 2 the sine of Sorry. Let me just do this so that we get all on the same page. Okay. It means that we'll say YA is equals to H over 2 the cos of theta P plus P minus T over 2 the sine of theta P. That is the y coordinate of point A, that one there. And that's basically how you calculate it. And we can compare our solution with what was calculated, as you can see here. That is a YA. See, H over 2 theta P plus P minus T over 2. It's pretty much the same as what we've calculated. And I see they continue to find only the y coordinates for different points before doing the x coordinates. But you don't necessarily have to follow that sequence. You can find both the x and the y coordinates of one point before you move to the next one, which is what I prefer. So by so saying, then I mean we can we might as well look at right now we can just move on to point D. Yeah. Okay, so now we want to find the x and the y coordinates of point D. And we'll follow still the similar procedure. I think in the point A, I was supposed to have showed you the x coordinate of point A. I'll do that in this slide here. Okay. So this is what we have. I'm just going to write the triangles that we used previously. We used this rectangle to determine that the vertical axis, and we also used this triangle here. Maybe I should use a different color. It is okay, hopefully. There we go. And we basically used that vertical line and that one to give us the y. And now for the for calculating the x coordinate of A. Let me just move things a little bit. To determine the, sorry, not the x coordinate, I'm referring to the x coordinate, but in this case, remember that we have z here and not y and not x. So that's y and then that's z here. Okay. So for A, we are looking at using this, to use the entire length and subtract that length there. Yeah, that's pretty much correct. So what this means is we will do it like as follows. We do know that this is B This is b minus t over 2. We want the x, and we know that this is theta p. We want this guy there, and that guy there. Excuse me. Okay, so to calculate that x part there, we'll just simply say that is b minus t over 2 the cos of theta p. This will give us that distance. Notice that the distance that we're calculating is from that point up until that point, but the z coordinate must be from that to that. So we have to subtract this distance there from that one. So let us calculate this distance. That distance there, that distance is that distance there. We know how much is, we know how much this line is h over 2, and we know the angle there. We can easily calculate this one. Okay, so that's h over 2, and that's theta p, and we can find that that side here of it, the horizontal part, and it will give us, let me use that basically will be equals to h over 2 the sine of theta p. So we're saying we subtract this one from that one will give us the z coordinate of point A. Therefore, we will have ZA is equals to, just zoom out a little bit, it will give us b minus t over 2 the cos of theta p. I'm going to just change the color here, minus h over 2 the sine of theta p. That's it, simple as that. And you can make the comparison, and that should it should give you the answer that we're looking for. But we now are supposed to now deal with point D and not point A. So let us have a look at point D. See if I can get some of these. Okay, it's fine. Now let's look at point D. Okay, I'll just try and use different colors because the drawing is getting cluttered. If we look at point D, we start off by finding the y coordinate. It means that we want that vertical distance. That's what we're looking for. We want this line, that distance. Okay, notice something really important here, that this line here is not the same distance as this one. This one is h over 2, we know, but this one is much less. So it means that we have to be careful of that. And these are some of the things that I wanted to indicate to you. The first thing that we can do, I would prefer that we use to determine the vertical distance of point D. We do the following, please bear with me. We basically use that distance, and then subtract that little bit that is there, that little bit here. So we use this entire length and subtract that small bit there. That should give us this one. So it's easy for us to calculate that one, and then from use that and subtract the little bit that is there. Okay, we already know how much this vertical one is. It's basically it's going to be that is going to be h over 2 the cos of theta p. That's what the distance will be, and we now want to subtract a small little bit. I'm going to have to zoom in here because otherwise we're not going to be able to see what I'm talking about. The little bit that I want us to remove is, let's change the color. Okay, there's a little triangle there. That distance there is the triangle. So this little bit is the one that I want us to remove, so that we only have that. So from this line we take that distance and we subtract this little bit, will give us that. This little bit, well, that's it. I'm going to just rewrite the triangle that little bit. Then we know that from there to there it's half of this thickness, and that is t over 2. So that is t over 2. And we know that that theta p is the same one as that angle there, this theta p. So we have theta p in there. Okay, let me just try that again. We put theta p in there. Okay, and we are looking for that distance, remember, that distance, and becomes quite easy. This is obviously going to be t over 2 as the sine of theta p. So now we know that we're basically going to subtract this one from that one, will give us the vertical coordinate, which is the y coordinate of point D. Therefore, we can say that yd is equals to h over 2 the cos of theta p minus t over 2 the sine of theta p. There we go. Okay, and that's just the y part, and the x part of D also quite interesting. It's just small details that we have to be careful of, nothing complex here, really. Okay, so we've now calculated the x coordinate, or the z coordinate rather, of point D. Okay, so then we can compare the solutions that we've determined. As you can see here, with point D, Z, D there. Oh, just notice that they've put the negative signs, obviously because the Z is on the negative side of the z-axis. That's the positive sign, so that needs to be negative. Okay. As you can see there. and the y is shown there. That is h over 2 the cos of theta p. That was the distance from there to there. You're subtracting that small bit that we were dealing with there. And really we apply the same approach to all the other problems. And when I say the other problems, I mean the other points. And we do the same for point D prime. If we move to D prime, and for point D prime, what it's a pretty straightforward. It's a really straightforward solution to point D prime. Remember that point D prime is that there. Excuse me. That there. Okay, so I'm just going to draw a triangle quickly. There's the triangle. There we go. Hey, it's a bad line. There we go. So this is straightforward. The reason I say so is because this will immediately be our y coordinate, and this will be our z coordinate of D prime. And we know what this is here is basically h over 2, and we also know that this part here is theta p. So therefore, we zoom out, we can confidently say that y d prime is equals to h over 2 the cos of theta p. Okay, and x d prime, no, not x, I keep referring to as x, but it's supposed to be z. D prime is equals to h over 2 the sine of theta p. Okay, and basically that's it. This is really basic analytical geometry, Pythagoras, okay, from really very basic mathematics. Okay, and we can compare this now also. We can compare the previous solution that we calculated to what was provided here. It's point D prime that we are looking at. That's D prime, and there's the solution. Obviously it's below it's on the negative side of the z, so it has a negative sign, and the y coordinate, the vertical distance, is above the z axis, so it's definitely on the positive side. That is why we have that as positive. So, and that's it. Okay. We will do the same thing for points. So for points E and E prime, they share the coordinates with point D and D prime respectively. So what I mean is E shares coordinates with D, and whereas E prime shares coordinates with D prime. The only difference is the sign of the values in their coordinates. I won't spend too much time there. Now we have determined the x and the y coordinates of all the points. It means now we continue further towards calculating the normal stresses at each of those points. So now we look at the bending moments, okay, of each point. Now we break the bending moment into two components, and please note that the arrow that is shown here does not indicate force, but it indicates the direction of the moment according to the right hand rule. And the right hand rule requires that you use your right hand and you basically make sure that your thumb is pointing in the same direction as the arrow, and your remaining four fingers, the direction in which they are pointing will give us an indication of whether that surface, the surface that the four fingers are hitting or going into, that surface will be experiencing compressive forces, as in this example here. So what this means is that if we look at this one here, if using your right hand rule, the four fingers will be going into page, and it means that everything on top of this z-axis will be seeing compressive forces, compressive stresses rather, which is negative. As I've previously mentioned in the preceding slides, knowing the direction of the components of the bending moment is important. So why is it important? This will make it easier for us to know the direction, either positive or negative, of the normal forces acting at one point due to each of those components of the bending moment. So therefore you must understand how to obtain the direction of stresses, i.e. compressive or tensile stress, the compressive being negative and tensile being positive. We are given the angle at which the resultant moment is acting. That angle is theta. Therefore, we can easily use Pythagoras to determine mz and my. Finally, we can now calculate the normal stresses at each point because we know we have all the necessary information to calculate the normal stresses. Let us look at a point to illustrate which component of the bending moment causes negative or positive normal stresses. Now, using the right hand rule, mz will result in compressive stress at point A, and my will also result in compressive stresses at point A. So to visualize this, imagine that you're using your right hand and your thumb is pointing in the direction of mz. Notice that your four fingers are going into the page, therefore compressing point A. Therefore it's seeing compressive stresses, which is negative. Now let's look at mz. This component of the bending moment, let's now evaluate whether it's going to cause compressive stress here or negative stress. You now imagine again that you're using your right hand and your thumb is facing the direction of these arrows. You will notice that your four fingers are going into the page on this side of the y-axis. And therefore every surface that is on this side will be seeing compressive stress because the four fingers are going into the page of this side of the y-axis. Therefore, this component will also contribute to the compressive forces of that point A. Therefore, both of them are negative, and they will result in a larger compressive stress. Now, Using the right hand rule, again, mz. Now let us now look at point D there. mz will cause compressive stress at point D. Why do I say that? Let's look at it. There's your mz. Use your right hand rule. Once your thumb is facing this direction of the arrow, you'll notice again that your four fingers are going into the page of this area of your cross section, therefore causing compressive stresses at point D. Now let's look at this component and see whether it causes compressive stresses there or tensile stresses. Imagine again that your thumb is facing the direction of these arrows. Look at where your four fingers are going. Are they going into the page of this side of the y-axis or this side of the y-axis? You'll notice that your four fingers are going into this side of the y-axis. Therefore, this side here, this side will experience compressive stress. Therefore, this side will experience tensile stress. Therefore, this bending moment, this component of the bending moment will result in tensile stress, which is positive on this side. This is important because it's going to affect whether you are adding or subtracting your normal stress at that point D. You will realize this a little bit later. And basically this is how the normal stress distributions would look like. It's not an obvious thing to visualize, but this is how it looks. The last thing we require to calculate is the angle beta, which tells us the orientation of the neutral axis. There is a derivation of a formula to calculate the angle beta, and this derivation is equation 640. It results in equation 641. Here we see the last part of the derivation of equation 641. So this is the part that is important for us. And this is the equation that we use to calculate the angle beta. That one. This concludes my video. You are most welcome to leave comments, suggestions, and criticism below so that I can improve on my next video. Thank you for watching.